Okay, so what if we wanted to include air resistance or some other force like friction, let's say, that would tend to slow us down? Let's take a look. So let's talk about air resistance. We've got, let's go back to the mass oscillating on a vertical spring, like in the Hooke's Law lab. MK, and suppose we stretch the thing some from equilibrium, and we start here. So we've got some, here's equilibrium, let's call that y equals 0, and here's y equals y maximum. And you know what? I don't know why I'm making life hard for myself. And then for myself and then for you. Let's use a horizontal situation. We've got a spring and a mass, and we're going to stretch it from equilibrium to something here. And here's our x equals 0, and here's our x equals x max. Let's assume that the floor here is frictionless, but now we want to include air resistance. No friction, but yes, air resistance. Okay, so we've got our mass, we stretch it, we let go. At some point here, right after we let go, we've got a few different forces acting. We've got the spring pulling us back the other way. Negative kx. According to our x coordinate, that's the elastic force pulling us back. But because we're moving this way, there's air resistance trying to push us the other way, trying to slow us down a little bit relative to the way that we're going. Because at this point, we're going that way. That air resistance is, let's assume we're not doing this very quickly and that we're talking about a low speed air resistance. So it's proportional to the speed with which we're going, which we know is a function of where we are. Oh God. This is all kinds of differential. Hold on, let's see what happens here. And we've got this B where this B is has to do with how strong the air resistance actually is. It's some kind of drag coefficient or something like that. So if we try to solve Newton's second law, F equals ma, then we've got minus kx plus bv equals ma. And now we've gotten minus kx plus b dx dt. If you remember, the rate of change of position is velocity. And a, which is the two rates. It's the rate of change of the rate of change. So it's the rate of change of the rate of change of position. This is, oh my gosh, this is even worse than the differential equation we ended up with last week. Yikes. It's a little bit beyond our scope, which is fine. But with a little bit of differential equations, we can show the form of the answer. It's still oscillation, but as we go back and forth, we lose energy because the air resistance slows us down. Eventually, we will stop. So with a little bit of diffie-q, we can show what that relationship actually looks like. And it's this equation. Some kind of amplitude, like we've had all along, and cosine of omega t, just like we've had all along. But this omega, it turns out, is slightly modified from root k over m, like we're used to. There's this sort of drag term inside the square root. As we increase how strong that air resistance is, we change slightly the frequency with which the system actually oscillates. And I guess that makes sense, right? The more resistance there is, the more slowly it'll oscillate. The other new bit is this exponential term here, which handles the energy loss due to getting pushed against by air resistance. Again, with a little bit of differential equations, we can prove this result. And if you really like taking derivatives, you could take two derivatives of this expression, this function. Remember that we're going to need the product rule and probably the chain rule a couple times. But you could, if you wanted to, plug those derivatives into this expression and show that they satisfy this version of the differential equation, this version of Newton's second law. I'm not going to do that, but you could if you wanted to. So I want to take a look at what this thing actually does. And by the way, these Desmos graphs, I will link for you when I post the content. So the amplitude, I just set it to 1 for, ease. I picked a mass and I picked a spring constant. And the interesting thing I want to talk about is this sort of drag coefficient, the air resistance strength number here, B. If we let it, so right now it's 1, and you can see that the oscillation has an amplitude of 1, but then an amplitude of about a half, and then an amplitude of about 50.2, and then about 0.1, and the amplitude, the size of this oscillation decreases, and eventually will stop if I zoomed way out the x-axis. If we increase the strength of the drag of that resistive force, we can get that oscillation to sort of, die out earlier, right? So now it sort of looks like we stop oscillating altogether around 7 seconds in, whereas before we were still oscillating past 10. Okay, so we could keep increasing the strength of the air resistance and keep sort of attenuating, trimming that amplitude. Here we've got a really quick reduction in the amplitude. It starts at 1, and then after only a second, we're something like an amplitude of 0.2. So we've got a 5-fold reduction in only 1 second. So we were oscillating a lot, and then we've slowed way down, and we're only oscillating a fifth of what we were. If we keep increasing, eventually we get to a point where we're not actually oscillating at all. We just have an amplitude, we've stretched it, and we let go, and it just stop. Like we just return to equilibrium slowly. Think about like a door coordinator, a door closer. What we really want to have happen is for it to close quickly, so that we don't, so whatever climate control isn't screwed up, but that it doesn't slam. Ideally, we'd like it to close kind of quickly and then gently latch shut. And that's called critical damping. excuse me, if we allow it to return to equilibrium as quickly as possible without oscillating, we're talking about critical damping. Anything less than that, and we've got an underdamped situation. We're still allowing oscillation, just not a lot. What if we overdamp? What if we damp, D-A-M-P? What if there's too much damping? And oh shit. what what happened to the graph? What happens if the value of b gets too large? What happens if this term, b squared over 4m squared, becomes actually larger than k over m? Then the subtraction means that there's a negative number under the radical, which is a thing we can't do. We're starting to imagine stuff. And there's a diagram in the book that instead of just quickly returning to equilibrium sort of as quickly as possible, critically damped, we get a slower return. It's something like something much less steep at the beginning, something sort of like this. And then there's a diagram in the book that shows that. Let me see if I can find it really quick. There's one. Okay, so the curve C is the one that I'm talking about, where it's overdamped, so it's going to take too much time to get back to equilibrium. B is going to get us there quickly as we can, critically damped. C is going to take too long to get back there. Under, critically, overdamped. The last piece on this Desmos graph that I want to talk about is the this sort of exponential piece. And if I turn that graph on, I think you'll see what it's doing. It's tracking the sort of the region in which the oscillation lives. It's actually it makes more sense, I think, to take this piece and put it with the amplitude term. Because those pieces are the amplitude pieces. This exponential part, e to the negative blah, 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 is what helps restrict the amplitude. So this is like it's the, I'm going to call it the envelope in which the amplitude has to occur. And as time goes on, that argument gets larger, and e to the negative larger gets a smaller thing. So as time goes on, the amplitude has to live in a smaller and smaller envelope. And that's that decrease that we're looking at. Okay, so that's damped oscillations. What if we had a damped oscillation, but instead of just stretching the spring and then letting go, what if we kept pushing it? What if we pushed it with not just a single direction force? You know, if we strapped a little rocket to this mass so that it was being thrusted that way, you know, we'd let go and it would get pushed this way, and then the rocket would it wouldn't oscillate. The rocket would just try to keep it going that way, and eventually we'd get to a point where the spring was compressed so much that whatever thrust was coming from the rocket the spring was pushing back equally strong and it wouldn't go anywhere. I'm thinking about, like, what about pushing someone on a swing, right? If we're trying to push a pendulum, right? So we've got the thing swinging, or we're on a swing and we're trying to get it this way, or pushing someone on a swing set. So we give them a push and they swing out and then they swing back. And the next time we should apply some force is when they've already reached us and we're pushing them back away again. If we try to push them too early, right? If as they're swinging back towards us, we put our arms out, we're just going to get smacked in the face with the person on the swing. That there's a frequency, there's a proper interval that we should push with to get a maximum amplitude response. If we actually want to increase the size of the swing, we should only push every so often. And you can try this trick on a swing set if if you can find a park that's open right now. Make sure to social distance, though. Maybe this isn't a great idea. Um, you can imagine trying this on a swing set, and with doing the thing where you kick your legs back and where you kick you extend your legs by straightening your knees to push yourself forward, and then you bring yourself backwards by bending your knees, and you have that sort of periodicity to it. But what if you bend your knees at the wrong time? Then the motion gets all weird and you kind of slow down, your amplitude drops way off. We are aiming for resonance, that we are applying a force at just the right frequency, the frequency omega with which the system already wants to oscillate. If it already wants to oscillate at this frequency and we try to get it to do that, then it's like, hey, I'm happy. Yeah, let me all the amplitude. This is my sweet spot. But if we try to push the swing at a different frequency, the system is like, what? Why are you trying to get me to do that? I don't want to do that. I want to do this other thing. Maybe an example would help.
As you can see, this bridge was exceptionally long and narrow, over half a mile long, only 39 feet wide. It lasted just 4 months. During construction, we see the steel girders, 8 feet tall, which were supposed to stiffen the bridge against bending. However, some up and down vibration was observed during the entire useful life of the bridge. Here's opening day.
We see that word resonance.
On November 7th, the bridge suddenly went into a twisting motion. The wind speed was a steady 42 miles per hour. This was enough to keep the bridge oscillating in one of its natural modes of vibration with a period of 5 seconds.
The wind speed, 42 miles an hour, apparently, is like our pushing force that as for the swing set. It happened to be pushing the bridge, strumming it almost like a guitar string.
A professor of engineering went out to see what had happened. He's coming back, walking with some difficulty along the nodal line, which is the center stripe of the roadway. It's remarkable that the girders were this flexible. This is photographed at normal speed. However, a collapse was inevitable after a little more than an hour of this.
Skip ahead a little bit. I'll link to this video so that you can watch at your leisure. Okay. So the deal here is that we happen to be, the wind happen to be pushing, driving this oscillatory system at just the right frequency, at what I'll call the natural frequency, the frequency with which the system wanted to oscillate. And we get this huge peak in the amplitude response, enough that we apply too much stress to the material and it eventually fails. So again, with a little bit of differential equations, we can show what the amplitude in this case, this is the amplitude of oscillation as a function of driving frequency. So this is not the same as this function. This is position as a function of time, and I'm not using that coordinate system anymore. I just want to talk about the amplitude of the oscillation that results when we push with a force of 10 newtons at a frequency that I'm using the x variable for. So as x changes across the horizontal axis, we're tracking the amplitude of the response. And we get this fantastic peak here right around 2.5 radians per second. That together with the spring constant and the mass and the damping, that's the frequency with which we get the biggest response. As we change B, the stronger the resistance is, the more damping in the system, the smaller that peak becomes. It also shifts to the left a little bit, but the size of that amplitude response decreases kind of rapidly. If the system isn't very damped, then we can get huge peaks in the amplitude. You know, this is an amplitude change of a factor of 10 from low frequency driving, somewhere here down around y equals 1, to right at the natural frequency, y equals 2.5. We get 10, y equals 10. So we've got a tenfold increase in the amplitude of the system. And if this is a bridge, you know, oscillating at 10 times the normal amplitude is, yeah, it's going to do exactly what that bridge did in Washington. Okay. On to the next thing.